Rational numbers are numbers which can be written as fractions. However, these fractions can also be expressed as decimals. If you wanted to see examples of this, just enter any fraction in your calculator as a division problem, hit enter, and it should give you the decimal value that equals that fraction. Some of these decimals are terminating, meaning that they end after a certain number of digits, and some are repeating. These continue on forever with the same digit repeating over and over. Your calculator will usually round a repeating decimal. It won't be able to display all of the values, of course, but it will be able to display all the values of a terminating fraction or a terminating decimal if there are few enough digits. Alright, so here are some examples. If you enter the fraction 1/2 in your calculator as 1 divided by 2, right, this will generate the decimal 0.5. Right, so that is a terminating decimal. It ends after one digit after the decimal place. All right, and another example would be, how about 3/4? Okay, a little longer. This one gives you 0.75. All right, repeating decimals. Things like 1/3. All right, this is really 0.3333 forever. Oops, make that a little nicer. 333, repeating. All right, and you may remember that we can write this as 0.3 with a bar over the 3 to show that the 3 continues on forever. I could also do that really at over any of the 3's, right? So this is the exact same thing as if I had written 0.33 with just a bar over 1 3, or I could show that they continue in groups of 2, something like that. The repeating decimal 0.66, or I'm sorry, 626262, continuing on forever in that pattern, could be expressed as 0.62 with a bar over the 62 to show that they repeat in groups of 6's and 2's. Alright, so let's look at some examples of terminating and repeating decimals, and let's show how to convert these back into fractions. So the terminating ones, you could probably do this on your calculator if you have a decimal to fraction key. If not, here's the process that you would use. Alright, so I'm going to do this using place value. Right, so this is the tenths place, hundredths, thousandths, 10,000ths place. Alright, so what that would mean, if I was going to read this decimal in words, I would say that this is 3,447 10,000ths. Okay? And I could write that as a fraction, 3,447 10,000ths. And I would just place that over 10,000 in the denominator. Alright, I do want to always reduce fractions to lowest terms. Right, so this one, right, it looks like it's going to be hard to reduce, but it's really not. And the nice thing about fractions like these is that your denominator is always going to be a power of 10. It'll be 10 or 100 or 1,000, 10,000. And if I was to look at the number 10,000, I'll do this off to the side here, and kind of start factoring this down. This is 10 times 1,000. 1,000 is 10 times 100. That's 10 times 10. And all of these 10s are 2 times 5. So if I was to look at the prime numbers that divide into 10,000, I only have two options. Right? It's divisible by 2, and it's divisible by 5. And if 10,000 is not divisible by 2, then it certainly wouldn't be divisible by 10. Right? And the same goes for even a complicated number like 3,447. The only numbers that I really need to check to see if this can be reduced would be the numbers 2 and 5. Because if that's not even divisible by a 2, then it's definitely not going to be divisible by a 10, because a 10 has a 2 in it as one of its factors. Alright, and if you remember, there's an easy test to see if something is divisible by 2 or 5, and you would just check the last digit. Right, if the last digit is an even number, it is divisible by 2, and if it's not, then it's not. Right, so this is not divisible by 2. to check if it's divisible by 5, you would see if the last digit is a 0 or a 5. And if so, then it is divisible by 5. Alright, so this one is not. And I don't need to check any other numbers. I don't need to check if this fraction could be reduced by 3 because I already know that 10,000 is not divisible by 3. And the reason I know that is because if I look at all of these prime numbers, I don't see any 3s. I don't need to check numbers like 12, right? Because 12 has a 3 in it. And my 10,000, I already know that that doesn't have a 3, so it wouldn't have any of the multiples of 3. It wouldn't be divisible by 6 or 9 or 12 or 15, anything like that. Right? So I'm only really needing to check to see if this is divisible by 2 or 5. So that means that this fraction is in lowest terms, and I don't really care if the numerator is divisible by any of those other numbers. This very well might be divisible by 3, but I don't care because I know that 10,000 is not. Okay, and that is a fraction in lowest terms. All right, one more example. How about 0.52? Right, so again, I'll do this using place value. This is the tenths. This is the hundredths place. All right, so we always base our fraction off of the very last digit. Right, so that we would say that this is 52 hundredths. All right, and again, I'm checking to see if this can be reduced, and the only numbers I need to check are 2 and 5. All right, so 52 is divisible by 2. That's 26. And 100 is divisible by 2. And dividing, I get 50. And it looks like I can go one step further. Still checking for 2's and 5's. 26 can be divided by 2. And so can 50. All right, so my final answer would be 13 25ths. And I can stop since 13 is not divisible by 2 or 5. All right, what about a number which is larger than 1? All right, 8.5, and I'll give you a couple ways to do this. One option is to say, okay, I know that that's 8, and then the 0.5, using place value, that's 5/10. Right? I know that that's 8, and the 5/10 can be reduced to 1/2. Right? And then if you remember the steps for changing this to an improper fraction, I would say that this is, I would do 8 times 2 is 16, and then I would add in the 1 to get 17, and I would say that this is 17 over 2. Right? I think that's the long way. Here's a slightly shorter way, perhaps. All right, 8.5, I would still use place value. This is tenths. And I would just say that this is 8.5, or I'm sorry, let's back up here. Okay, notice right now this is over 1. 8.5, we can always think of something as being divided by 1. Right, so I have a fraction right now. The only issue is that I still have a decimal in there. I'd like to get rid of that decimal. So if I multiply the numerator and denominator by 10, I would get 85 over 10. All right? And then the only thing that I need to do there is to put that in lowest terms. All right, so I can divide each of these by 5, and I get 17 over 2. Okay, so same thing, and that's a fraction in lowest terms. All right, how about 9.32? All right, so one option, this is 9.32, and right now it's just over a 1. All right, and then think about how many place values I would need to move this decimal point to get rid of it in the numerator. And I would need to move that 2 places to get a whole number. All right, so I'd like to do that. I'd like to make this 932. And in order to do that, I need to multiply by 100. So I would do the same thing in the denominator. Multiply by 100, which essentially moves that decimal 2 places. And then I would go through the steps to reduce this fraction. All right, so I can see that this one's divisible by 2 because the last number is even. All right, and dividing by 2, I get 466. Okay, and then in the denominator, 100 divided by 2 is 50. All right, that can be reduced again by 2 again to 233, and then 50 divided by 2 is 25. And I can stop. My last digit is a 3. That is not divisible by 2 and not divisible by 5, and those were the only two numbers that I was checking for. All right, what do we do about repeating decimals? So 0.3 repeating, or 0.3333, etc., etc., etc. All right, so some of these you may have memorized. We already talked about this one, 1/3. But for the ones that you don't, because your calculator rounds these numbers, in other words, your calculator is going to display this as 0.333 for a while, but then it will eventually stop. And so this is actually not the repeating decimal. This is an approximation. This is a terminating decimal that's displayed on your calculator screen. So if you were to use that number and choose your decimal to fraction key, you're not going to get the exact answer. You're going to get an approximation. In this case, all right, you're going to end up with that number over, right, and this is tenths, hundredths, thousandths, 10,000ths, 100,000ths. Right, and that's not actually the original decimal. That does not equal 1/3. Right? So we actually do have an algebra process that we can use to find the exact fraction that a repeating decimal does look like. All right, so let's try this. Let me erase this. Okay. All right, so here's what we do. We're going to use the letter x, the variable x, and we'll say that x equals our original fraction, or our original decimal, 0.3 repeating. Okay? So what we want to do in the end here, we want to get to the point where we have x equal to some fraction. In this case, we know it's going to be 1/3. And then I could say that because I know that, I've just kind of rewritten x in two different ways, I would then know that this decimal is the same as my fraction 1/3. Okay. The next step is to multiply x by a power of 10 that has the same number of zeros as the digits that are being repeated, as the number of digits. All right, so I have a bar over one number so that I know that just one number is being repeated in this decimal. All right, so I'm going to multiply x by 10. All right, and I'm going to write that above. All right. Now think about this decimal. This is 0.33 repeating forever. All right, and if I multiply that by 10, that's just going to move the decimal over one spot, but then I still have all of these 3's repeating forever, and I haven't really changed that fact. Right, I've just moved one more of them to the left of the decimal. So that would actually equal 3.3, and it would still be a repeating 3. All right. And we did use an algebra fact here, the fact that we can multiply both sides of an equation by the same number. Right, so we can multiply both sides by 10, and the equation stays the same. Right, and remember, you can kind of think of an equation as a scale, right, that's balanced. Right, so if you do something to one side, if you do the same thing to the other, then it keeps the equation equal. All right. The next thing that I want to do is subtract these two equations, and that's another algebra fact. We can subtract equations. All right, so on the left I have 10x's, and I'm subtracting 1x, and I get 9x. All right, and then on the right, when I go to subtract these repeating 3's, all of those 3's are going to line up and continue on forever. And there will be the same number of them, right? So these 3's cancel, these 3's cancel. 3 minus 3 is 0. 3 minus 3 is 0. All right, forever, and those are all gone, right? So that's going to be a 0. And then I just have 3 minus 0 in the 1's place. 3 minus 0 is 3. All right. Now to solve this equation for x, this is 9 times x, so I need to divide both sides by 9 so that I get x by itself. Right? And notice that works because 9 divided by 9 is 1. Right? And I know that 1x is just x. It can be written as x. Right? So x equals 3/9, and in lowest terms that would be 1/3. All right, so I've got two statements here. Originally I said that x was equal to 0.3 repeating, and now I'm saying that x is equal to 1/3, so it must be true that that decimal and this new fraction are the same number. All right, here's another example. We say x is equal to 0.44 repeating. All right, so this time we've got 4 4's, 4 and 4, 4 and 4, repeating forever in groups of 2. All right, so now I've got 2 repeating digits. All right, and actually, let's change this example a little bit, because I could really write that as just 0.4 with just 1 digit repeating, and so that doesn't really give you a new example. So let's change this to maybe a 0.46. All right, so this is really 0.46, 46, 46, etc. Okay. So now I have 2 distinct digits being repeated infinitely. So I'm going to multiply by a power of 10 with the same number of zeros as my 2 digits, or in other words, by 100. All right, and on the right, what I'm essentially doing here is moving the decimal point 2 places to the right when I multiply by 100. Right, so that's going to give me 46.464646, still 46 repeating forever. We've got all of these 4's and 6's left. Okay, and then I will subtract. Right, on the left I have 100x minus 1x, and that's 99x. And on the right, I have all of these 4's and 6's repeating infinitely, and all of them are going to subtract and equal 0. Okay, so every 6 minus 6 is a 0, every 4 minus 4 is a 0, etc. Okay, 6 minus 6, 4 minus 4, those all become zeros. And then I'm left with 46 minus 0, which is 46. All right, and then to solve for x, this is 99 times x, so I would divide by 99. All right, and 99 divided by 99 is 1. So that leaves me with 1x is equal to 46 over 99. Okay? So I have a fraction. I need to make sure that it's in lowest terms. All right, if you think about the denominator here, again, that's a little bit easier. Okay, your numerator will vary, but your denominator, when we go through this process, is always going to be a 9 or a 99 or a 999. And if you break that number down, okay, that's 11 times 9, and 9 is 3 times 3. So we're going to have a bunch of 3's, and in many cases an 11, something like that. All right, so in this situation, I just need to check if this number is divisible by 3 or by 11. And looking at the numerator, 46 is not divisible by 3. Okay, and you can use a calculator to check that. And it's definitely not divisible by 11. So this is in lowest terms. All right. Now, you should always be able to check these to see if your answer is correct. So on a calculator, just enter 46 divided by 99, and your calculator should show you 0.4646 repeating. And at some point it will probably round. It may round the 4 up to a 5, or it may just cut off at some point. So it would be hard to go backwards to get your fraction, but you can start with your fraction that's your answer and check to see if it matches the original problem. Okay, here's another one. This one has 4 repeating digits. Okay, so I'm going to multiply by 1 with 4 zeros, or 10,000. All right, and that's going to give me, I'll move the decimal, I'll be able to move it 4 places to the right, so I will get 6179 point, and then in my decimal, the numbers that continue on after that would be 6179. So you can kind of see why we're multiplying by the power of 10 that we are. We want the repeating part of this number to line up. Right? So if I only move the decimal point 3 places over to the right, then I would have 617 before my decimal, and then my repeating part would start with that 9 and then go into the 6179. And then when I try to subtract, they're not going to line up and they're not going to cancel. Okay, so move it 4 places to the right, so it's 6179.6179, 6179, repeating forever. All right, again, subtract. 10,000x minus 1x is 9,999x. And on the right I have 6179, and all of these repeating decimal values subtract to be 0. Okay, and then finally dividing both sides by 9999. Okay, and I get x equals 6179 divided by 9999. I do need to check if this is in lowest terms. The only prime numbers that go into the denominator are 3 and 11, so I'm going to start there. Okay. You may remember the check to see if something's divisible by 3. If I add all of the digits in the numerator, I can, and if the sum is divisible by 3, then my number will be as well. Right, so let's do this. Let's do 6 plus 1 plus 7 plus 9. Right, and that's 7, and 7 is 14, and 9 is 23. And 23 is not divisible by 3. All right, there is a divisibility test for 11, but it's a little long, so instead I would probably just use a calculator, and I'm going to do this now. 6179 divided by 11, and it looks like that is not divisible by 11. Right, so I can stop there. That is in lowest terms. Okay, so that's my final answer. All right, one final example. Okay, so we'll start out the same. X equals 0.632 repeating. Okay, now in this case I only have one digit that's being repeated, so I only need to multiply by a power of 10 with 1 0. So 10x equals, right, my decimal is going to move 1 place to the right, and I will have 6.32, and then it's the 2's that are repeating forever, none of the other numbers. Okay, and then I subtract. All right, so 10x minus x is 9x. All right, on the right, my repeating 2's cancel. All right, and then 2 minus 3 I'll need to carry a 1. 12 minus 3 is 9. 2 minus 6 I'll need to carry again. 12 minus 6 is 6. And 5 minus 0 is 5. And I do have a decimal point in there, 5.69. Okay, dividing both sides by 9. All right, you'll get x equals 5.69 divided by 9. And then I do want to get rid of that decimal. So we haven't done an example like this yet. But I would like to just have a fraction without any decimals involved. Right, so I need to move the decimal point 2 places to the right. And I can do that by multiplying by 100. And then in the denominator I just get 900. All right, So to check, to see if this is in lowest terms, I know that 900 is 9 times 100. I already know that the only prime numbers that go into 100 are 2 and 5, and the only prime factors that go into 9, the only one would be 3. Alright, so 5, 6, 9, I just need to check if it's divisible by 2, 3, and 5 to begin with. Alright, so using my trick for the 3's, if I do 5 plus 6 plus 9, alright, that's going to be 20. That's not divisible by 3, so neither is 569. And I can see just by looking at the last digit that it's not divisible by 2 or 5. Okay, so that is in lowest terms, and that's my final answer. And to check, if you enter that in a calculator, 569 divided by 900, you should get 0.63 with as many repeating 2's as your calculator will hold.